Hello guys. So this lecture will be about our last topic um, before the final exam. So we kind of start at the end of last lecture. Um, so I think we don't have to spend the full 1.5 hour to go over this law, which is the Ampere's law. So just a quick review of what we did last time. So to use Ampere's law, let's consider this situation where we have a piece of wire, like in the first picture here. Okay, so when the wire is oriented vertically like this, and what we do is we want to see how the magnetic field at each point are pointing. So we put a small, a few compass around the wire. So these compass normally we just point to the north, right? Because there's no other magnetic field. The only magnetic field present is the one from the Earth. So it's pointing to the north, which is indicated by this arrow here. So let me zoom in a little bit. So every compass will just point that way. Okay. But now what happens when we start to pass some current through the wire? Let's say the current is going up. Then we see that the compass no longer point to the north, which is that direction. So now it's going around like a circle. And this is what we say in the last lecture, that the magnetic field is going around in a circle. That means at every point along this circle, the magnetic field point in the direction tangential to the circular path around it. And you have two choices, right? Whether it's going this way, like in the diagram, or it's going the other way. So if you look from the top here, right, you're gonna see the current either, not the current, the magnetic field either going clockwise or counterclockwise. The one shown in the diagram is going counterclockwise, right? So it's going that way. To find the direction of the magnetic field, you have to use the right hand rule. So the thumb points in the direction of the current, and you kind of grab the wire with your other four fingers, and the direction of your fingers tells you the direction of the magnetic field. Okay, so in this case it's going like this. Okay, so last lecture we talked about how we can calculate magnetic field from the Biot-Savart law. That's gonna be something that people use more often, but it's a little bit hard to use. There's another law which we talk about at the end of last lecture, which is called the Ampere's law. So today we're gonna talk exclusively about this law. Even though the practical use of this law, the Ampere's law, is quite limited, but there are some important application that we can use the Ampere's law. So if you can use Ampere's law, it's going to be a lot easier to calculate the magnetic field, but not every situation can be used, okay, for the Ampere's law. So that's kind of the same deal when we talk about Gauss's law for electric field. Okay, so what is Ampere's law? Ampere's law is written in this form. So it's the integral of B dot dl equal to mu 0 times I, right? So let me walk you through like what this means. So in order to use the Ampere's law, first you need to choose a closed path, right? what does it mean? It means that you have to choose the path where it ends up where you start from. So you cannot choose the path where it's not closed, which is something like this. So this is not gonna be applicable for Ampere's law. So it has to be a closed path, and this is the reason why we have this small circular kind of symbol in the integral sign, is to indicate that we are integrating along this closed path. Right. For example, look at this situation here. The path we choose can be a circular path which goes around the wire and then end up where we start with. So it's a circular path which is closed by definition. Okay, so you choose a closed path, and then you can start walking at anywhere in the path, let's say like there. Okay, so you walk a little bit along the path. So when you walk along the path, you have some small displacement along the path. Right, displacement is a vector, so I can write small displacement dl and vector sign here to indicate that it's a vector. And during this small displacement, you have to see what's the magnetic field you measure at that point. Right, so I'm going to use the green vector to indicate the magnetic field vector. So at this time, at this point, the magnetic field is pointing that way. Right, so it's pointing tangential to the circle. So that means the direction of the magnetic field and the direction of the displacement, small displacement, dl, they point in the same direction. That's gonna be important because at every point you need to calculate. So I'm gonna write it here. So calculate a dot product between the magnetic field and small displacement dl, right? So only during that small displacement you need to calculate this dot product. So in our particular example here, they point in the same direction, right? B field point along the circle, and dl is also along the circle because dl has to point along the path that you have chosen from the beginning. So in our case, the dot product becomes just B times dl, right, because they point in the same direction. So if you remember, the dot product actually contains the cosine term, where this angle is the angle between the two vectors. Like in this case, the angle is 0 degrees, right? So cosine of 0 is 1. So that's why we don't need to include the cosine term in this dot product. But in general, you might need to consider whether the cosine of the angle is really 1 or something else. But it can also be 0. Okay, so once we have this, then you calculate the integral b dot dl, which now becomes just b dl, right, because of the dot product being just b times dl. Okay, so what do you do exactly here? Well, you need to do the same thing at every point on the path. So as you go along the path, you have to write down dl. Again, for example, if you walk already here, then dl is pointing that way, right? So because we are walking along the circular path. And magnetic field, so I should use blue here. So dl is like this, and magnetic field also point that way, right? So at every point on the circle, the b vector and the dl vector point in the same direction. And because of the symmetry of the problem, the magnetic field has the same magnitude every point on the circle because it's the same distance from the wire, right? Because the circle, every point on the circle is the same distance from the center of the circle, which is pretty much the radius of the circle, right? So that makes the integral is really easy because in this case, B, the magnetic field, the magnitude of the magnetic field is a constant. Okay, so going back here, then what I can do is I can take b out of the integral sign because b is constant, right? So be careful here. When I say b is constant, I mean the magnitude of b is constant. Of course, the direction is not constant. The direction has to go around in a circle, right? So at different point on the circle, it's gonna point to a different direction, but the magnitude is the same. But here, the dot product already kind of take care of the direction, so we only need to care about the magnitude here. So I can take b out. Then what I have left is the integral of dl. This is nothing but the total distance along the path that we have chosen. So in this case, the path is going around in a circle, so this one is just the circumference of the circle. So altogether we have b times 2 pi r. So this integral is really simple. It's just b times 2 pi r, right? So then in the end, what we need to do is we need to write the right hand side of this Ampere's law, which is mu 0 times I, right? So what is mu 0 times I? Well, mu 0 is the constant, which we covered last time. Is called the permeability. Well, I mean, if you don't think too much about that, it's just a number, so nothing to worry too much about. And the current here is the current passing through the loop. So this is the loop or the path that we have chosen, right? So it's the current that passing through, which is the current carried by the wire, right? So in this case, we actually finish using the Ampere's law to calculate the magnetic field from infinitely long wire. So maybe I forgot to say that the wire has to be infinitely long, because otherwise you don't have all kind of symmetry that we talked about earlier. So I will summarize it here. So the B field, the magnetic field from an infinitely long wire that is carrying a current of I is given by, so the magnitude is given by mu 0 I divided by 2 pi r. So r is the distance from the wire. Okay, and the direction is given by the right hand rule, just like in this picture. Okay, so it depends on where you are on the circle. Magnetic field, so B field point tangential to the circular path around the wire. So you can see that Ampere's law is very easy in this case. It tells you the magnitude of the magnetic field, which is inversely proportional to how far away from the wire as 1 over r. Okay, and the direction you have to use the right hand rule to figure out. Okay, so this is probably the most important application of Ampere's law. The other one that we need to talk about is solenoid. So a solenoid is something that we have probably seen in, well, a typical experiment that involves electromagnets will have a solenoid. So what is a solenoid? So if you look at this kind of diagram, which is kind of like a build up of what can be done in terms of magnetic sources. Okay, so what we just talked about in the previous page is the magnetic field from infinitely long wire, which is the first diagram here, right? So remember, this means the magnetic field is pointing out from the page. This is pointing into the page. So this is consistent with the right hand rule. Okay, and the magnetic field strength is exactly what we just calculated using the Ampere's law. Okay, and then what you can do also is you can make, instead of a long wire, you can make it in a loop like this. So this one is a cross section of a loop. So a loop is just like a ring. So you can make you can bend the wire to make a single loop, and the magnetic field is given by this formula. Okay, so if you have many turns, right, given by n turns, then the magnetic field at the center is given by this. Okay, r is the radius of the loop. Okay, so this is B at the center, which is magnetic field right at this point. Okay, so if you are a little bit far away from the center, then the magnetic field will be weaker. So you have to use the Biot-Savart law to calculate that. Okay, in any case, it's more practical to not use just a single loop, but a solenoid, which is a coil essentially that consists of many loops. Okay, so it's like a a typical heating coil that some of you probably have seen. So from the side way it looks like that, but if you have a solenoid that is not so close to each other in terms of like each individual turns, it might look something like this. Okay, so the green arrow around this diagram indicates the magnetic field, right? But most of the time we're gonna talk about a solenoid which is kind of like ideal solenoid. So ideal solenoid is so an ideal solenoid essentially is kind of like very long, so long that we can almost assume they're infinitely long. But I mean, as we have seen many times, nothing is infinitely long, but if it's long enough, then it's a good approximation. And also there's no gap between turns, right? So this one is definitely not an ideal solenoid. So the one we have up here kind of looks like an ideal one, though it doesn't look that long. Okay, but it's okay. So our goal here is to find the magnetic field inside the coil, inside the solenoid. Okay, so what do we do? So if you think about this diagram and then you make a slice through half of the coil, so what I have here is I'm gonna have like this small circle. So this one are the wires that being cut across the solenoid, right? And then of course you also have the other side like this, right? So then essentially it's gonna something like this. So I'm not gonna draw that because that gonna make the diagram too crowded, right? And if you look at how the current travel in each coil, so I can say the coil at the top has the current going like this way. Okay, so let me zoom in a little bit. So this means the current is going out from the page. Okay, so I'm not talking about the magnetic field, right? I'm talking about the current, but we use kind of the same the same symbol for saying that the current is going out from the page, right? So if you imagine that the current is going around in a loop, right? So it's going out from the page, then it has to come back here. So come back there, that means the current has to go in at the bottom, so we can draw like X here, right? So the current going into the page at the bottom like this. Okay, so it's gonna be like this at every point on the solenoid. So remember, we assume that the solenoid is infinitely long or like very, very long. So it doesn't matter like where you look at, the solenoid is gonna be the same. So the magnetic field inside the solenoid will be going to the right. Okay, so why going to the right? You have to go back and look at this picture, right? And this is something that probably you need to convince yourself that magnetic field is indeed going to the right in this direction, right? So if it's in this diagram, it means the magnetic field is going up, right? So I just kind of flip this 90 degrees, then you're gonna get the picture that I drew here, which means the magnetic field is going to the right. Okay, so another thing that we gonna find, but it's actually a little bit less obvious, is that the magnetic field is the same everywhere, no matter where you are in the solenoid. So that means the magnetic field here is the same as here, it's the same as here, and it's the same as here. So everywhere. So this is what we call a uniform magnetic field, right? So uniform magnetic field means the direction is the same everywhere. The magnitude is also the same everywhere. So we want to find the magnetic field strength inside the solenoid. So we're gonna try to use the Ampere's law. Okay, so you remember how we're gonna use that. First, you need to decide what kind of closed path that we're gonna use, right? So the path that we're gonna decide to use is a rectangular path that goes like this. Okay, so it's a little bit funny like why we are doing something like this, but we want the bottom one, the bottom side of the path, to be as far away as possible from the coil, because if it's far away, then the field, the magnetic field from the coil, is going to be zero. So that means we don't need to worry about B.dl for the section on the wire like here, right? So here, so very long, so this very long, so that means the green section here, B.dl, will be 0 because B is almost 0 when you are very far away from the coil, right? And another thing that we can say is that because of the symmetry, the magnetic field along this path, and also the one inside, so the side of the rectangle here, because the solenoid is very long, right? So it doesn't really make sense to have magnetic field to have the component in this direction sideways. There shouldn't be any field. If there's any magnetic field, it has to be in this direction, so vertically, right? But as you go around the path, right, you're gonna have the direction of dl going down this in this side of the path, but then when you go around and then you come back onto the other side, dl will point in a different direction, so it will point up, right? So in this case, any b.dl you have on this side will get cancelled out by the one next to it on the other side, because dl, the direction of dl flip. Okay, So even if you have like a non-zero magnetic field that gives you B dot dl at this point to be non-zero, then this point here will give you exactly the same value but negative sign. So in the end, the contribution to B dot dl, the integral of B dot dl, will be not from here, not from here, not from here. So the only one that we need to worry about is the one here inside the coil, right? So this is the only contribution of B dot dl that we need to calculate. Okay, so then let's zoom in a little bit in that section. Okay, so let me draw again the wire going like this. So remember, this wire has the current going in, so it's gonna be X, right? And the path that we chose for Ampere's law is gonna be something like this. Okay, and again, the only path that we need to worry about is the one on the top here, right? So if the length here is L, okay, so let me rewrite. So if the length here is L, then the magnetic field integral of B dot dl, remember all the contribution from the side and the bottom here is, they are all zero, so we don't need to care about them. So the integral of B dot dl is simply just B times the length of this section, which is L. Okay, and this equal to mu 0 times I, right? But this I is the total current that is passing through the loop created by us in the beginning. So there's not only single wire going through, right? So if you look in the diagram here, at least we have like 1, 2, 3, 4, 5, like we have 5 times the current, right? So let's say we have like n turns, in the loop, right, entrance in the loop, then this one is not just I, you have to replace it by times n. Okay, so this n and this n is the same one, okay, the number of turns in the loop. Okay, so we have something like this. So we have like B times L equal to mu 0 I n, like this. Okay, so what we're gonna do is we're gonna put L on the other side and write n over L, right? So instead of telling how many turns exactly, because it depends on how long the solenoid is, right? So usually instead of telling you how many turns, we're gonna use this number, which is turn per length, LENGF, of the solenoid. Okay, and we're gonna use a small n to indicate that. So B equal to mu 0 I times small n. So this is gonna be the formula for the solenoid. Okay, so it depends on how much current you put in, what is the number of turns per length of the solenoid. So you can see that if you wind the solenoid so that each turns are very close to each other, so you have many turns per length, then you're gonna have a stronger magnetic field in this case. Okay, so so in other words, let me summarize it here. So the magnetic field from an ideal solenoid is simply V equal to mu 0 I n. Okay, and this is the magnitude again, and the direction is gonna be like what we said in this diagram. Okay, so you can also use the right hand rule to figure out like which way the magnetic field is pointing. So you can curve your forefinger around the direction of the current in the coil, and then you will see that your thumb will point in the direction of the magnetic field like this. Okay, so the right hand rule is actually very robust in this topic, because I mean it can apply to every case that we have talked about. Okay, and the field is also uniform, so that means same magnitude. Okay, same magnitude and same direction. Okay, everywhere inside the coil or the solenoid. Okay, and we also assume that if the coil is long enough, the solenoid is long enough, V equal to 0 outside the coil. Okay, so all the magnetic field will be confined within the inside of the solenoid. Okay, so that's pretty much it about the topics that you need to know for the final exam. The remaining videos will mostly be problem solving, so so stay tuned, and then I will let you know again when the next one is up. Alright, I'll see you in the next one.